Hey everybody. So in order to understand some things, everything in the universe, we need to take half a step back and talk about some basic concepts of physics, like motion and gravity. If we can get a basic handle on how anything in the universe moves the way that it does, and how gravity works in general, then we can jump back into planets and stars and talk about and get a better handle on how they work in specific. So let's talk about the basic question of why do things move the way that we see them. And the funny thing is, when you dig through the history, it's not exactly an obvious answer. People worked for millennia to try to get a handle on, like, why do objects move the way that we see them? And the first person to get a decent handle on the answer to that was Galileo. Because Galileo, on top of his experiments with building telescopes and recording what he saw in his telescope, Galileo also ran a whole bunch of experiments on trying to figure out how do objects move and why. Why do they move the way that we see them? And after trying a bunch of different experiments, Galileo came up with a first principle for why objects move. And he called that principle inertia. That his basic answer, Galileo's basic answer to why do objects move the way that they do, is because they're already moving. That inertia is to say objects want to keep on moving the way they're already moving. That objects in the universe are lazy. The word inertia is just Latin for the word laziness. Objects in the universe are lazy, and they want to just keep on doing what they're already doing. If an object isn't moving, it wants to keep on not moving. Things in the universe don't just start moving on their own. So that if an object is changing its motion, if an object goes from not moving to moving, or if an object goes from moving to moving faster, any change in the state of an object's motion must come from some force. What is a force then? A force is any phenomenon. A force is anything that causes the motion of an object to change. That in the absence of any forces, things just keep on moving the way they were already moving, under their own inertia. Which turns out to be surprisingly simple and yet very effective at explaining why do objects move. Things just tend to keep on moving the way they were already moving. And so, if an object's motion is changing, there must be some force acting on that object to change its motion. If an object in the universe is moving, and it slows down until it eventually comes to a stop, like in the case of friction, right? Friction tends to cause things to slow down and then stop. So, friction changes the motion of an object. It gets it from moving to not moving. Therefore, friction, by definition, must be a force. The nice thing about astronomy, the nice thing about space, is that there isn't a lot of friction out there. That things, if you get something moving, it just tends to coast. So if you fire a rocket and shoot it out into space, it's not like there's some friction rubbing it against the ground to slow it down. If you fire a rocket out into empty space, it'll just coast. Or, if a planet starts flying around the sun, it's not like it's going to slow down, it's just going to keep on coasting around the sun, under its own inertia. So, Galileo sort of started these arguments about why do things move. Oh, things move because they have inertia and or because some force is acting on them. And then a couple of generations later, Isaac Newton picks this up, and he takes these ideas that Galileo and other people in the meantime had to try to explain motion. And Newton tried to boil it all down into some basic principles. What are the basic principles that describe why anything moves? And Newton codifies them. Newton boils it all down into 3 basic laws for why anything moves the way that it does. And so understanding Newton's laws of motion help us get a handle on why anything moves the way that we see them do it. And so to understand the physics of motion, we need a little bit of vocabulary here. And I think I want to clarify the vocabulary because words in physics don't always mean exactly the same thing as they do in everyday English. And so usually when we use these words in physics, they don't have the flexibility that everyday English does. They mean something much more specific. So, for example, okay, speed, what is speed? Speed is just how fast something is moving, right? It's how far you can travel, what distance you can travel per unit of time. If you're driving down the road at 60 miles per hour, you're going to travel 60 miles of distance in 1 hour of time. So that's pretty much the same as it means in everyday English. Velocity is not just speed, right? In everyday English, velocity, speed, they're synonymous. But in physics, velocity means your speed plus the direction that you're traveling in. So your car might be driving at 60 miles per hour. The speed is 60 miles per hour, but your velocity could be, for example, 60 miles per hour south. Why does it matter? Well, because Newton's first law of motion is essentially just reiterating Galileo's law of inertia. Newton's first law says a body at rest tends to stay at rest, or a body in motion tends to maintain that exact same motion unless they're acted upon by an outside force. So, just like Galileo's law of inertia, objects want to just keep on doing what they're already doing. So, in this case, if you've got 3 balls on a table, ball A is not moving, and it's just going to keep on not moving. Ball B, if ball B is rolling across the table, it's just going to keep on rolling across the table with a constant speed in a straight line. In other words, if ball B is rolling across the table, it's going to maintain a constant velocity, right? Constant speed and a constant direction. It's just going to roll in a straight line. Ball C is rolling across the table, but then when it gets to the middle of the table here, I'm going to poke it with some force. I'm going to exert a force on it, and because I push on the ball, it changes the ball's velocity. Either it changes the speed, maybe the ball speeds up, maybe the ball slows down, or it changes the direction. But the velocity is the speed and the direction, so that if the speed or the direction changes, that means the velocity changes. So another way of rephrasing Newton's first law is to say an object will maintain a constant velocity. It'll keep going at the same speed, or no speed at all if it's at rest, and it'll keep going in a straight line unless that object is acted upon by a force to change the velocity. If an object's velocity is changing, there must be a force causing that change. So what is a force? A force is any phenomenon that changes the velocity of an object, either the speed or the direction, or both. Newton's second law says that the acceleration that an object experiences is proportional to the force that's being applied to it, but the acceleration is inversely proportional to the object's mass. Okay, so now we've got a little bit more vocabulary here. What is acceleration? What do we mean by acceleration? Well, acceleration, there at the bottom of the page, acceleration is how fast an object's velocity changes. It is the rate of change of velocity. So acceleration is how fast the object speeds up, or how fast it slows down, or how fast the direction changes. Or both, right? The mass we've already talked about, right? The mass of an object is how much matter it's made of, how many atoms, how many particles it's made of. So In other words, if there's a force pushing on an object, that object's velocity is going to change because there's a force applied to it. How fast the velocity changes, how fast the object accelerates, is proportional to the force. If I push harder, it'll speed up faster. But the acceleration is inversely proportional to the mass. If I'm pushing on an object, the more massive the object is, the more inertia I have to overcome, so it's going to speed up slower. It'll have a slower acceleration. So, what is acceleration? It's the change in velocity. So, you could rephrase Newton's second law to say how fast the acceleration changes is proportional to the force, but inversely related to the mass. Newton's third law says that forces always come in pairs. This is usually phrased as the famous, for every action there's an equal but opposite reaction. To be more realistic about it, though, what Newton's third law says is that for every force, there's an equal but opposite force. So if object A is exerting a force on object B, like if I push against a wall, well, then that wall is going to push back on me, right? If I push on the wall to the left in this picture here, if I push on the wall to the left, well, then the wall is going to push back on me to the right, and then my body will accelerate off the wall to the right. And those two forces, your body pushing against the wall and the wall pushing against you, those two forces will be equal in strength and opposite in direction. The harder you push against the wall, the harder the wall's going to push back on you, the faster your body is going to accelerate pushing off the wall. Forces always come in these action-reaction pairs when one object exerts a force on another. Alright, so these three laws, Newton's three laws, they apply for any force, any velocity. They explain how any object moves the way that it does. So when Newton figured this out, Newton figured out, okay, why does anything move? Everything moves the way that it does because it has some inertia and it just wants to keep on moving the way it does, or because there's some force acting on it, or both. So once Newton had got that nailed down, then he changed his view to say, okay, well, if I can explain how any object moves, can I explain why the moon moves around the Earth? Why does the moon orbit around the Earth? If an object wants to just keep on moving in a straight line, if objects want to just move with a constant velocity in a straight line under their own inertia, then why doesn't the moon move in a straight line? Why does the moon move around the Earth? And he said, well, there has to be a force. If an object's direction, if the direction of an object is changing, its velocity is changing, and a change in velocity requires some force. So there must be some force between the Earth and the moon causing the moon's velocity to change around the Earth. And that force, he called it gravitation. People have known about gravity, right? People have known, we're stuck here on the Earth. The Earth pulls us down. People knew about the concept of gravity since time immemorial, but Newton was the first person to say, to sort of explain it in terms of a force between two objects. And here's the thing. Newton's theory of gravity, Newton's theory to explain how gravity works, is a universal theory. Gravity is not just a force between the Earth and the moon, or between the Earth and the sun. Newton says gravity is a force between every two objects in the universe. Between your body and the Earth, your body and the moon, your body and the sun. Every object in the universe is pulling on every other object in the universe with this gravitational force. and that gravitational force just happens between two objects based on their masses and based on their distance. Right? Gravity is not just a special property of the Earth or the Sun, because Newton is saying there's nothing special about the Earth, there's nothing special about the Sun. Gravity is a property of every object, because the laws of physics are the same everywhere. Newton's laws of motion apply to every object. Gravity is a property of every object. Everything attracts everything else. And that the force, okay, now we're getting a little complicated here, so let's unpack what's going on here, right? The gravitational force is a force between two objects depending on their masses. So if you've got two objects, the blue object here has a mass, we'll call it m1. This object, the green object, has a mass m2. These two objects are a distance r apart. The distance from the center of m1 to the center of m2 is a distance r. And Newton figures out that the gravitational force between them is equal to m1 times m2. So the mass of object 1 times the mass of object 2. But the gravitational force, the strength of the gravitational force, is inversely related to the distance between them squared. So that two objects are, move my face out of the way here, F1 is the force on object 1, F2 is the force on object 2. So that object 1 exerts a force on object 2, and object 2 exerts a force back on object 1. And those two forces are equal in strength and opposite in direction. Just like every force is. It's an example of Newton's third law. So that the force on 1 and the force on 2 are equal in strength, but opposite in direction, because gravity always pulls things together. Gravity always tries to attract objects together, which is how you get these two forces being equal in strength and opposite direction, trying to pull them together. That the force of this gravitational attraction is equal to m1 times m2. So it is proportional to the product of their masses. The more massive the objects are, the stronger the gravitational force between them. But the gravitational force is inversely proportional to the distance, so that the farther apart they are, the weaker the gravitational force is. You take all of these things and you multiply it all by this big G. This big G is technically what's called the universal gravitation constant. It's basically a number. Big G is a number that is baked into the universe. It is the number that determines how strong the gravitational force is in our universe. And so it's a constant. It's a constant of nature. And it's a pretty small number. It's 6.67 times 10 to the negative 11. So gravity is a pretty weak force when you have objects that are low mass. Gravity only becomes the dominant force in the universe when you talk about objects that are substantially high masses. Planets, stars, galaxies. But gravity is a force between every two objects in the universe. There's a gravitational attraction between your body and the computer screen in front of you. It's there. It's just not very strong, because your body isn't very high mass, the computer screen isn't very high mass, and then you multiply them both by this tiny number, big G, so that the gravitational attraction between you and every object in this room is negligibly weak, but it's not zero. So Newton says, okay, if this is true, if there's a gravitational pull between every object and every other object, how can we use this to explain the moon's motion around the Earth? And Newton constructs a thought experiment. What is a thought experiment? A thought experiment is basically a what if, right? I'm not going to actually run this experiment in the world or in a lab. I'm just going to say, what if I did this, what would happen? So Newton says, what if I took a cannon to the top of the tallest mountain in the world, and I just fired that cannonball horizontally? Well, if you fire this cannonball horizontally, the cannonball's inertia is going to want it to go to the left, but the Earth's gravity is going to pull it down to the ground. So how does the cannonball go? The cannonball goes left and down, right? Inertia wants to carry it to the left. Earth's gravity wants it to be accelerating toward the ground, so it moves left and to the ground. If I fire this cannonball a little faster, it's going to have more inertia, and its inertia is going to carry it even farther to the left before it hits the ground. If I fire this cannonball even faster, pretty soon the curvature of the Earth is going to become significant here, and that cannonball might go so far that it lands behind the horizon. If I fire this cannonball even faster, then we need to plot this trajectory by saying, okay, at every instant, when the cannonball's right there, its inertia wants it to go this way, but gravity wants it to accelerate toward the center of the Earth. And so it goes down toward the ground and forward until it gets here. And when it gets here, its inertia wants to go forward, but acceleration wants to pull it to the center of the Earth, so it goes down and forward. And at every instant, this cannonball is falling toward the ground under gravity, but its inertia wants to go forward. So it goes forward and down, forward and down, forward and down, until if you fire this cannonball fast enough, it could land clear on the other side of the world. If I fire this cannonball even faster, conceivably I could fire this cannonball so fast that it falls all the way around the Earth and hits Newton in the back of the head. This cannonball could fire so fast that as it falls toward the ground, the Earth's ground curves away from it, so that as this cannonball falls, it doesn't actually get any closer to the ground. As it falls around the Earth's curvature falls away from it, and so the distance between the cannonball and the ground stays constant. This cannonball is basically going so fast that it's falling toward the ground, but it just misses the ground entirely. It falls all the way around the Earth and hits the cannon one orbit later. Because that's what this is. This is an orbit. An object is in orbit if its inertia wants it to go forward and gravity wants it to go down, and yet as this object is falling toward the Earth, its inertia carries it forward so fast that it just misses the ground and goes around the Earth instead of going down to the Earth. That's what an orbit is. Gravity wants to pull everything toward the center, toward each other's centers, right? Gravity wants two objects to be pulled toward each other. So why, if there's a force, if there's this gravitational force between the moon and the Earth, why aren't the moon and the Earth pulling each other together? Why isn't the moon crashing into the Earth? And the answer is because it's going forward fast enough. The moon has enough speed, the moon has enough inertia, that its inertia wants to carry the moon forward so that it is falling around the Earth and not falling down to the Earth. That's what an orbit is. Right? An object stays in orbit around the Earth as long as it is flying forward fast enough to miss the ground, close the loop, and come back around. If it's not going fast enough, then it'll happen to happen to any projectile. If it's not going fast enough, it'll crash into the ground. But if you can fall so fast, if you can move forward so fast that the curvature of the Earth never intersects with you, you stay in orbit. An orbit is a path curved by gravity. realistically, how do you do this? Well, in order to get into orbit realistically, you got to get above the atmosphere, right? Because in order to stay in orbit, you got to keep going fast enough. And atmospheric friction, or drag, slows you down. So if you want to put a satellite or a cannonball, or if you want to put anything in orbit of the Earth, you got to get above the atmosphere so that you can keep going at a constant speed under your own inertia and not slow down. The top of the atmosphere is about 200 kilometers straight up. So if you want to launch a satellite in orbit of the Earth, you got to get up high enough to be above the atmosphere, which isn't the hard part. Our atmosphere is really not that thick. The atmosphere is only 200 kilometers up. So getting a satellite up that high is the easy part. You got to get it up above the atmosphere, and then you got to get it going sideways. You got to get it moving forward fast enough that it falls around the Earth and doesn't fall back down to the Earth. And that minimum orbital speed is about 17,000 miles an hour. This is why rockets have to be that big. When you're launching a satellite into orbit of the Earth, a satellite is not that big, but you've got to get it up high enough and going forward fast enough that it doesn't come crashing back down. And getting a payload going at 17,000 miles an hour requires a lot of thrust. It requires a big rocket with a small satellite on the very tip of it. If you can do that, though, if you can get high enough and get going sideways, get moving forward fast enough, that object will just fall around the Earth and not fall back down to the Earth. And it'll stay in orbit. So that's how Newton figured out why why is the moon orbiting around the Earth? Is that what's keeping the moon in orbit around the Earth? Gravity is what's holding the moon around the Earth, but why isn't the moon crashing down to the Earth? Because it's got enough inertia. It's moving forward fast enough to stay in orbit, to stay falling around, and not ever intersect with the Earth's surface. Hopefully that gives us some basic understanding of how gravity works in general, how orbits work in general, how motion works in general. So once we start talking about the orbits of planets around stars, or the orbits of two stars around each other in a binary system, those are all going to happen according to gravity. So keep this in mind for the rest of the semester. If we can keep a basic handle on how gravity works in general, it's going to make a whole lot easier to talk about how gravity works in specific systems in astronomy. Thanks, everybody. I hope this made some sense, and I'll talk to you later.